Hi, I'm Dave Taddeo, and this is Coders Tech. This isn't going to be a regular episode of Coders Tech, but I want to talk a little bit about the Sapphire iPhone screen. I've been following this. I watched with interest when Apple announced that they were going to be building Sapphire production plants and so on and so forth, because they wanted to make a nice big screen for the iPhone 6 and iPhone 6 Plus. And I was wondering if they'd ever worked with Sapphire before. And I laugh about that a little bit because I've worked with Sapphire. As you might be able to see from my website, if you click on it, most of you probably don't care what's there. It's a very niche industry. But I'm a coding guy. And because I'm a coding guy, for the last 25 years, I've had the opportunity to work with Sapphire quite a bit. With Windows, all kinds of optics that Sapphire is used for. Sapphire is a great material for a lot of the reasons that the press has been talking about. It's very, very hard, very, very scratch resistant. It's transparent in a wide wavelength range, right down into the UV, up in probably just past the mid-wave IR range. And so it has a lot of applications. But I've worked with Sapphire. I've held Sapphire. I've looked at Sapphire. I've read drawings with Sapphire, drawings for Sapphire optics and stuff, optical specifications and so on and so forth, physical specifications. And I was really interested in the fact that Apple was going to make Sapphire screens. This is extremely difficult to do. Anybody that's worked with Sapphire, anybody that's held Sapphire, anybody that's had to look at very closely on an optical level, you're making optics, so you really have to look at these things. You have to clean them. You have to check them for all kinds of blemishes and so on. Working with Sapphire is extremely difficult. First thing, it's very, very hard. And that's one of the reasons Apple wanted to use it. It's a very, very hard material. But because it's very, very hard, it's very, very difficult to polish. It takes a long time to polish. Something like Gorilla Glass, anything like your regular optical materials, some of them very hard. Polish takes some hours to days sometimes to polish, especially if you're looking for flatness, if you're looking for parallelism, if you're looking for scratch dig, if you're looking for blemish-free, no sleeks, things like that. So polishing something like Sapphire is extremely difficult. You have to use diamond labs. You have to use diamond slurry because nothing else is really going to polish it in a production kind of time frame. And remember who we're talking about. We're talking about Apple. Apple is looking for very, very high quality. So they're looking for very small scratch dig or to no scratch dig. Their scratch dig specifications are probably 0.0. Is what you probably get on your regular Gorilla Glass phone is a 0.0 scratch dig. But when you're polishing something like Sapphire, you're polishing it for a day, you're polishing it for 2 or 3 days to get a nice surface on it. If you take that off there, the optician takes that off of the polishing pad or the lap and sees that there's a scratch, a 5 scratch, a 5 dig. That's not going to pass specifications for quality, for aesthetics, especially for a company like Apple. If you do have a small scratch, a 5 scratch, a 5 dig on Sapphire, you put it back in, you start to polish again. This takes hours or days to get that out, and then you risk the fact that you're going to scratch and dig it again. Remember, we're polishing with diamond. Even though Sapphire is hard, diamond's harder. You need to use diamond to polish it, and so on and so forth. So Apple's looking for aesthetics. They're looking for optical quality like scratch dig. You also have birefringence in Sapphire. So Sapphire has a different different refractive index depending on the polarization of the light coming through. Now that may not be a big deal, especially when the light emitted from a screen like this, an LED backlit LCD display, is going to be emitting polarized light anyway. So if you get the crystal axis right, which you're going to have to do out of the furnace, you're going to have to know what your crystal axis is. If you don't, then you have to do that with X-ray diffraction imaging to find the crystal axis. Once you get the crystal axis, then you have to cut the piece to that size and then polish it to that size. So the birefringence might not make a big deal, might not be a big deal if you know the crystal axis and you place it on the screen so that the ordinary and extraordinary rays are coming through in a certain axis of that crystal. If you take a look at this screen here through some polarized sunglasses, you'll know what I'm talking about. Anybody that's taking pictures in the summertime that wears polarized sunglasses, you know, I go out in the summertime quite a bit and take pictures of stuff. And as soon as you take this screen and you put some polarization in front of it, as soon as you turn it into landscape mode, this is the effect that you get. You don't see anything. And so maybe polarization, the birefringence of Sapphire doesn't make a big difference or isn't a big deal because you're dealing with a polarized light source to begin with, an LED backlighting array with the LCD screen above it, so on and so forth. Even still, if you get your crystal axis aligned and if you can possibly even get a 6-inch screen, I mean, that's big. I mean, that's really, really big to go 6 inches. Now, this is an XS5, that's not quite 6 inches, but the iPhone 6, iPhone 6 Plus, that's a big surface area to get flat. I mean, you want to have quarter wave flatness on there. You know, I don't even have to have an interferometer to be able to look at my Gorilla Glass phone and see that it's probably not quarter wave flat. Parallelism as well, and so on and so forth. So this is a massive undertaking. This is incredibly difficult to grow aluminum oxide, sapphire, out of a furnace in a crystal axis, cut that to size, polish it over several days, and have it blemish-free. The optical surface is blemish-free, no scratch dig. The scratch dig spec is 00. No inclusions. So you look at a company like Zeiss, they say Zeiss is nice at twice the price. Well, you pay for quality. Zeiss lenses are very high quality. They choose their glass out of a big ingot of glass. They're looking for the spot that doesn't have any inclusions. So you would have to do the same with aluminum oxide. You know, I've never been in an aluminum oxide production facility where sapphire is coming out of a furnace like that, but there's going to be inclusions. There's going to be dislocations in the crystal structure. This is a massive undertaking. And it can only be my guess, based on my experience in the optics industry. You know, I may be a coder, but I've handled a lot of optics, including a lot of aluminum oxide and sapphire. I've seen what it looks like when good optics come out for laser applications, military applications. I know what it takes to make aluminum oxide or sapphire really, really good, very high quality optics. And in my opinion, it's my guess that that Apple didn't really understand what the cost of taking on such a project was going to be. Aluminum oxide can be expensive. I'm looking at a website where I'm going to show you. I'm looking at, this is Edmund Optics. If you work in the optics industry, everybody knows Edmund Optics. I have no affiliation with them, but I just picked this up because they show some stuff here. 25 millimeter diameter, so you've got an inch. Quarter wave flatness. Where did it go here? Quarter wave at 633 flatness. Surface quality, 40-20. A 40-20 scratch dig, I mean, that's insane. I mean, that's like looking at a pitted windshield almost. I'm exaggerating, but that's almost like looking at a pitted windshield, where the clear aperture is only 90% of this 1 inch. Thickness is 2.3 millimeters, so that's fairly thick. Getting optics very thin is very difficult as well. Very thin and parallel, so we have something that is parallel to less than or equal to 3 arc minutes. That's good. Not perfect, but good. Probably a company like Apple is looking for something that's a little more parallel than that. You can see here for this particular Sapphire window, the birefringence, the ordinary ray minus the extraordinary ray is 0.008 for visible light orthogonal to the optical axis. So you can see that this is a fairly high quality optic at 1 inch diameter, 2.3 millimeters thickness, with some decent optical quality to it. And they're asking for $195 each. This is not unheard of. Now, mind you, this is retail. This is from Edmund Optics. You could probably buy this in bulk, get it in volume for quite a bit less. But when you're talking about a screen for a phone that's going to be 6 or plus inches from corner to corner, you want to have this surface quality has to be 0-0. That's very difficult in the first place. Parallelism has to be probably better than 3 arc minutes. And the surface accuracy, probably something similar to that, a quarter wave at 633 nanometers. Like I say, when I looked at my Nexus 5, just by eye, just by looking at the reflection of the light, I could tell that it's probably nowhere near that. I don't need an interferometer to see that it doesn't look like it's a quarter wave at 633. So for $195 for a 1 inch diameter window at retail, you can imagine what Apple was getting themselves into. This is not a very easy thing to do. And as it turns out, it's probably going to be extremely expensive. It's going to be very time consuming. It's going to be very expensive. And if you think it's expensive at $950 for a single unit, when they're trying to push out 12, 15 million units, you're probably talking double the cost. And Apple probably wouldn't increase their profits very much off of such a device with a screen made out of sapphire. And production times, I mean, production times are going to be much longer because it is a lot harder to polish sapphire and aluminum oxide. And anyone will tell you, I talked about Zeiss. I mean, there's a lot of good companies that make very high quality optics. But most of them, if you're going to be an optician, you're going to spend 4 to 6 years as an apprentice to be able to polish something, super polish something like laser optics that are used in satellites for gyros and things like that. This is not a push button operation. You put in a whole bunch of polishers, you throw in a whole bunch of sapphire and hire a bunch of people at $14 or $20 an hour and say, push this button and show me some sapphire screens next week. This is an art. And I know that sounds a little bit weird, but ask any optician, especially when it comes to something like this size, this aspect ratio, that parallelism, the optical qualities, the scratch, the dig requirements for such a device. This is an art. This takes a lot of experience to be able to polish and get right. Anyway, I just wanted to kind of weigh in. I thought it was very interesting. I know they're coating their new screens with anti-reflection coatings, which is great because I mean, I can see the reflection off my screen here. So I'm looking forward to companies like LG and Samsung, you know, picking these things up and coating their screens with anti-reflection coatings. So that's just it. I just wanted to weigh in there and kind of shed some light on what Apple had to go through, and really what my opinion is on why it didn't work out. I think it's way too hard and way too expensive. Even if they've sorted out some of those issues like birefringence and having a polarized light source coming through a birefringent optical glass, and you know, polishing down so that your scratch dig is 0, it's going to be way too expensive and way too difficult. Okay, thanks for watching.